SystemVerilog clock to queue modeling. This video is about why we need non-blocking assignments in SystemVerilog. I talk about important timing parameters in flip-flops, clock to queue delay in practice, and non-blocking assignments. There are three important timing parameters in a flip-flop. Setup time and hold time are related to input data and clock. And clock to queue delay is related to input clock and output data. Now let's see what is setup time and hold time. Setup time is the minimum time that data must be stable before the clock edge. And the hold time is the minimum time data must remain stable after the clock edge. It means that during this time window, setup time plus hold time, data must be stable so that the flip-flop can sample data correctly. After the clock edge, the output data doesn't change immediately. It takes some time. This time is called clock to queue delay. In RTL simulation, we use zero simulation time. It means that we don't model timing parameters of flip-flop in RTL simulation because at this stage the functionality of design is important and we want to make sure that our design is work correctly. But there is a problem here. Without clock to queue delay, all input and output of the flip-flops change at the same time. It means that we couldn't model cascaded flip-flop in this case. Consider ring counter as an example. The circuit is shown in here. As you can see, the output of each flip-flop is connected to the input of the next flip-flop. And the output of the last flip-flop is connected to the input of the first flip-flop. So it's like this. At reset, the first flip-flop is set to 1 and other flip-flop are 0. So we have this at the reset time. At the clock edge, the data is shifted by 1 to left. So we have this, and at the next clock edge, the data is shifted by 1 clock to left, and so on. To model this circuit in RTL code, we need to model clock to queue delays because without clock to queue delays, all input and output of flip-flops change immediately, and the circuit doesn't work correctly in our simulation. The solution to this problem is using non-blocking assignment. Non-blocking assignment is introduced in Verilog and SystemVerilog to model clock to queue delay. We use arrow assignment operator for this purpose. The non-blocking assignments are scheduled into two phases, evaluation phase and update phase. The RTL code for the ring counter is shown here. In evaluation phase, the right hand side of the assignments are evaluated and it is stored in a temporary location. In update phase, all left sides are updated immediately from the temporary location. In this example, count 0, count 1, count 2, and count 3 are updated immediately, and they get the previous value of count 3, count 0, 1, and 2. By using the non-blocking assignment, we can model the clock to queue delay in SystemVerilog. So, by using the arrow assignment, we can implement this circuit correctly in RTL code. The take-home message is that without clock to queue delay, it's not possible to model cascaded flip-flop because all input and output change simultaneously. To model the clock to queue delay, we need to use non-blocking assignment. Non-blocking assignments are evaluated in two phases: evaluation phase and update phase. These two-phase evaluation make it possible to model the clock to queue delay of a real flip-flop. Thank you for watching this video.